Hi, my name is Matt Prelee, and I'm going to briefly describe my work with Dave Newhoff on multidimensional Manhattan sampling and reconstruction. A very quick overview is it's a classical sampling result where if an image or high-dimensional function is supported on the union of Nyquist regions, it can be perfectly recovered from the union of lattices corresponding to those Nyquist regions. So if we consider a two-dimensional example, we have a union of Nyquist regions. One is a horizontal Nyquist region and one is a vertical Nyquist region. And then we have lattices corresponding to those Nyquist regions. This horizontally dense lattice corresponds to this Nyquist region, and this vertically dense lattice corresponds to this vertical Nyquist region. Turns out you can recover an image that's band limited to this region from these samples. And furthermore, it's optimal in the Landau sense. We've extended this to high dimensions. I have two three-dimensional examples here. We have the union of what we call Manhattan lines. You sample densely on sets of parallel lines in 3 dimensions. A function can be recovered from these samples if it satisfies this spectral constraint. Another example is if a function satisfies this spectral constraint, it can be recovered from sampling on the faces of this cube in 3 dimensions instead of the edges of the cube. The way we do this is with an onion peeling algorithm. We call it an onion peeling algorithm because we reconstruct the high frequency arms first and then figure out how those high frequency arms alias the low frequency regions in the spectrum. And then we recover the low frequency regions. In higher dimensions, we would recover these very high frequency regions first, then the next highest frequency regions, and then finally, you can't see it here, but there's a low pass region that we would recover last. My last comment is that we proved this using a new notion of bi-step lattices and vectors. Essentially, we form vectors that are binary, where they represent both frequency regions and lattices, where the ith entry is 1 if the lattice is densely sampled in the ith direction, and we put the ith element of these vectors is 0 if it is coarsely sampled in that direction. And it leads to an algebra with nice properties that tell us which frequency regions we can recover first, and then which ones we can recover next. And it presents this very nice recursive structure that gives us our onion peeling algorithm. So that's it. This paper should be up on archives soon. Email me, mprelee@umich.edu if you have any questions. Thanks.
So good. Thank you.